Welcome back to our course on blockchain and its applications. So, in the last class we have seen the PBFT consensus algorithm. You have learned that how we can utilize PBFT to solve the Byzantine fault, rather to come to a consensus in the presence of Byzantine fault. So, today we are going to look into the safety and liveness properties of PBFT algorithm. So, broadly we are going to discuss about this what is meant by safety and liveness in the context of PBFT and how we can ensure safety and liveness in PBFT. So, remember that we discussed earlier in the context of FLP impossibility that we cannot satisfy safety and liveness altogether in the context of an asynchronous environment. Now, here we will see that how we are reducing or rather releasing that strong assumption of asynchronous network a bit to ensure liveness in the context of PBFT algorithm. And in that same notion, we are going to discuss about this PBFT view change, which is particularly used to ensure liveness in the protocol. So, these are the keywords for today's talk. Broadly, we are going to talk about this concept of weak synchrony in the context of liveness or to support liveness in PBFT, and then we are going to discuss about the view change protocol. So, just a brief recap about what we have learned till now. So, we have seen that PBFT works in three phases. So, initially the client sends the request message to the primary, and then primary starts a PBFT round by sending a pre-prepare message. So, that pre-prepare message is a broadcast to all the replicas or the majority of the replicas depending on the setup of the protocol. Now, once this pre-prepare message is broadcast to all the replicas starts looking into quorum. So, in the context of PBFT we have seen that we need to A+1 quorum to reach to a consensus. So, once the replica observes that they get the pre-prepare message and this pre-prepare message is a correct message, then they broadcast this prepare message, that is in the second round of PBFT. Now, once this prepare message is broadcast, then everyone observes that whether they have received 2A+1 message, and among that 2A+ message what the majority says, that basically in my consensus view. So, based on this quorum on 2A+1 messages, they finally broadcast this commit message. So, this is the third round of PBFT. So, this commit message are broadcast from the primary as well as all the replicas, rather all the correct replicas. Now, once everyone or all the replicas and the primary received to A+1 commit message and the quorum gives the consensus view, then that consensus information is sent as a reply to the client. So, the three rounds of PBFT broadly are these three steps, that is the pre-prepare, prepare and followed by commit. Well, so in this three round this PBFT algorithm works. Now, we are going to look into that how safety and liveness is ensured in these three rounds of PBFT algorithm. So, to understand the notion of safety in PBFT, let us try to revisit this concept of safety in Paxos. Earlier we have seen the safety property of Paxos, and we have seen that in case of Paxos, we had a major difficulty because there can be multiple proposers, and when multiple proposers starts proposing certain message, then there can be a context where you will be having a ping pong effect. So, depending on the value of the ID that is being sent by the proposer. So, it might happen that proposer 1 sent a value, sent an ID, and that ID is something that the other responders have agreed to ignore. So, they do not send any reply back. So, the proposer send a new ID, and now this new ID is bigger than what the other nodes have committed. So they sends a response message. In the meantime, another proposer can send another another message with a higher ID, and that ID is being accepted by the majority. So that way there can be a kind of ping pong effect in context of Paxos. But in case of PBFT, we have an advantage that we do not have such kind of multiple proposers. Here the leader works like a proposer, because the leader proposes the message. Now, when the leader proposes the message, in the context of PBFT, we have a single leader. Well, so that is our advantage here in the case of PBFT. Now, because I have a single leader, we do not have any kind of ping pong that we have observed in the context of Paxos. So, we do not have such kind of ping pong among multiple replicas. However, in context of Paxos, what we have seen in context of PBFT, what we have seen that we need this 2a plus 1 quorum. Well, so we need 2a plus 1 votes for the prepare and the commit messages to reach to the consensus. So, that is the kind of requirement that I have. And whenever you have this 2a plus 1 nodes and you reach to a quorum, then this PBFT it reaches consensus, and it current round of consensus that gets complete, and it can starts with a new round. Well, so if I just try to analyze the safety properties, so what we see that PBFT is safe with 2a plus 1 quorum, because the leader can always have the majority votes to support its proposal that we have seen earlier. Whenever we have f number of faults, and this f number of faults, as we have seen earlier, that include the crash fault and the Byzantine fault. What we have seen that when I have f number of Byzantine fault, even in that case I will get f number of wrong messages, but with 2a plus 1 quorum I still have a plus 1 correct messages. Now, whenever I have this a plus 1 correct messages, I can guarantee that I will reach to consensus. In the same line, what happens that whenever I have f number of crash faults, then I have 3a plus 1 that many number of nodes in my network. So, I have 2a plus 1 messages, and ideally these 2a plus 1 messages they are coming from the non faulty nodes. So, all of them should agree. So, I can reach to a consensus. So, that way if I just rely on this a plus 1 quorum, 2a plus 1 quorum in the context of PBFT, I am always safe when I have f number of faults that includes both the Byzantine fault plus the crash fault. Okay. So that way we can ensure that PBFT is always safe in an asynchronous environment. And remember that this 2a plus 1 quorum, that is corresponds to this asynchronous environment. So, in an asynchronous environment, this 2a plus 1 quorum ensures that your protocol is running safe. So, that way because we are considering this asynchronous system, we understand that the leader can reach to the consensus even when it does not receive message from some of the replicas due to such asynchronous nature of the channel. So, if you remember the definition of an asynchronous environment. So, in an asynchronous environment, I do not have any upper bound on the message latency or message delay, and because I do not have any upper bound on the message latency or message delay, it can always happen that I receive a message long after it has been proposed, but with this 2a plus 1 quorum we see that it is safe to assume that whenever I have such kind of f number of faults which can include both the crash fault as well as the Byzantine fault, then I can have at least a plus 1 non faulty messages. So, whenever I have a plus 1 non faulty messages, I can ensure that whatever these non faulty messages are proposing, that is something the view at the safety. So, that way my consensus protocol is safe. it always reaches to a view that is being supported by the majority of the participants in my network. Well, so that way the safety property is ensured, but the question comes that what about liveness? Well, and the FLP impossibility told us that you cannot ensure safety and liveness altogether. Well, so just by remembering FLP impossibility, we can say that, well, we have seen that safety can be supported in an asynchronous environment with 2f+1 quorum. So, I can immediately say that, well, in an asynchronous environment I cannot ensure liveness. Well, but you may ask me the question that why liveness cannot be ensured, that what is preventing the protocol to ensure liveness? Well, so the environment or the scenario that is preventing this liveness is that we have assumed that the primary is non-faulty. Well, whenever we are running the protocol within a view. Well, but what if the primary is faulty? Because it is not necessary that the replicas will only fail, although we are selecting a primary depending on certain factors, but there is always a possibility that the primary may fail. Well, now whenever such primary fails, during that time the liveness get hampered, because primary is the proposer here, primary is going to propose the new message. So, if the primary fails, then in my network there is no one who can propose the message, and when there is no one who can propose the message, immediately the system cannot make any progress. Well, so it cannot go move to a next round to have a new proposal from the primary, because the primary has failed. So, this primary failure, that is something challenging in the context of PBFT, because primary failure cannot be handled in a pure asynchronous system, because you do not know whether it is a message delay from the primary or a primary failure. Well, say assume that I am a replica. Now, whenever I am a replica, what I am doing? I am waiting for a message from the primary. Well, now whenever I am waiting for a message from the primary and I do not receive a message, then there can be two scenarios. Either the primary does not have any message to send. Now, even if the primary does not have any message to send, another context can be that the primary has failed. Well, now when the primary fails, the primary is also not sending any message, but I can think of that, well, the primary does not have any message to send, so the primary is not sending any message. Well, so that way, if I do not receive a message from a primary, I cannot say as a replica that whether the primary has failed or whether there is no message to get forwarded from the primary. Well, so that way I cannot make any further progress. Well, and in a pure asynchronous system, remember that you can have arbitrary delay. Now, because you can have arbitrary delay, I have to wait forever. I cannot say that, well, I have waited for last 1 hour and within that last 1 hour I have not received any message. So, I can assume that the primary is faulty. That I cannot do in a pure asynchronous system, because in a pure asynchronous system we assume that the messages can have infinite delay. Well, so the message may receive, I may receive the message tomorrow, or even I may receive the message after 1 month. Well, that is not practical, but theoretically it is always possible. Well, now people started thinking of, rather the designers of PBFT, they started thinking of that, well, see, this pure asynchronous environment, this assumption is not very practical. Well, so even if you are in a slow network, even if there are multiple different failures in your message, and depending on the network protocol like TCP, which keeps on retrying the message, on such an environment, it might there would always be a kind of upper bound on the message delay. Well, you cannot have a kind of infinite delay in the message. Well, so that kind of practical environment is being considered in PBFT, and this is one of the reasons that PBFT is called practical Byzantine fault tolerant. Well, so for liveness, rather than considering a strong asynchronous environment, we consider something like a weak asynchronous environment. So, as we have seen that primary may fail in a strong asynchronous environment, and I cannot say whether the primary has failed or whether the primary does not have any message. So, what we do to support liveness in PBFT, we reduce the strong assumption of asynchronous environment and we assume something which is called weak synchrony. Well, now what is weak synchrony? Weak synchrony assumes that both the sender and the receiver are correct. Well, so it first assumes that the sender and the receiver are not faulty. So, the fault is on the network side. So, what is that? That the sender keeps retransmitting the message until it is received. Well, so that way even if there is a failure in the data transmission, say assume that in an intermediate router there had been a buffer overflow because of which the packet has been dropped and your message has not been received by the final receiver. So, sender keeps on retransmitting the message, something like a TCP. Well, so I guess that you already know the different kind of network protocols, and in the network protocol we have this TCP, that TCP supports something called the reliability. So, with all practical purposes we typically assume a protocol something like TCP that can support this kind of reliability. Well, so that way the sender keeps on retransmitting the message. Now, if the sender keeps on retransmitting the message, if it is a practical network, then eventually you are going to receive the message, that is going to happen. Well, say for example, in a TCP kind of network you are not receiving the message because there are some kind of intermediate congestion in some routers. So, that kind of things are there, right. But here in this particular assumption, even in a practical network it cannot happen that your network is congested forever. So, TCP also has its own congestion control mechanism. So, eventually your network will come out of the congestion and the packet will get delivered. Well, now with this what we do, that we consider an asymptomatic upper bound on the message transmission delay. So, we assume that well all my messages will be received within this time duration t. Well, so this particular threshold we assume, and this threshold can be chosen depending on your network condition. You can think of t as a kind of 3 second, or you can think t as a 10 minute. Well, so whatever you want you can just assume depending on your network condition, but what you assume that well you are surely going to get a message from a node within this time bound. Well, so what we are doing, that we are just releasing this weak synchrony assumption, strong asynchronous assumption a bit. Well, we are saying that the network is behaving something in between the synchronous network and the asynchronous network, right. So, in a synchronous network we assume that the message will be received immediately, and in an asynchronous network we assume that the message will have arbitrary delay. Well, so in one case there would be no delay, and in the second case there can be infinite delay. Well, now this weak asynchronous assumption actually balances between these two. Well, so it says that well you might not receive the messages immediately, there would be a time bound t within which you are going to receive the message. Well, so your delay bound is not infinite, it is not 0, rather some value t. So, that is why we call it as a weak synchrony network. Now, with this weak synchrony assumption we are going to ensure liveness in the context of PBFT. So, let us see that how we ensure liveness. To ensure liveness, PBFT proposes a protocol which is called a view change protocol. So, what is this view change protocol? View change protocol basically handles the case when the primary is faulty. So, this non-faulty replicas they detect the fault. Now, you might immediately ask me a question that what happen if there is no message for the primary to send. Now, just for this modification what PBFT does, that PBFT ensures that well PBFT periodically, the PBFT primary it periodically keeps on transmitting dummy messages even if it does not have any message to send. Well, just to say that hey I am live, but I do not have any meaningful message to send. Well, just like that I am saying you that hey, I am live. Well, it is not like that I am dead. Well, you will eventually receive a message from me. So, I am just periodically saying you hello, I am there. Well, so that way we can keep on sending such periodic what we call as typically a heartbeat message if the primary does not have any further message to send. Whenever the non-faulty replicas they do not hear any message from the primary, that can be a legitimate message, that can be something like this heartbeat or the hello messages within a time duration t, then it assumes that the primary is faulty. Well, and when the replicas detect that the primary is faulty, then the replicas together start this view change operation. Now, this view change protocol provides eventual liveness. So, it allows the system to make progress when the primary fails. Now, as I mentioned earlier that if the primary fails, then the backups will not receive any message or will receive faulty messages from the primary in case the primary is Byzantine. Now, these view changes are triggered by the timeout. That is my weak synchrony assumption that I have a time limit t within which you are going to hear any node. So, that way if you are not receiving any message from the primary within that time duration t, you can assume that the primary is faulty. So, it prevents backups from waiting indefinitely for request to execute. So, these backups they start a timer when it receives a request and the timer is not already running. Now, if the timer is stopped, so whenever certain request is executed, then you stop the timer, otherwise you restart the timer when some new request comes. Now, whenever this timer has expired, that means you have not received any message within that time duration. So, you start this view change protocol. Well, so if the timer expires at view v, then the backup starts a view change to move to the next view v plus 1 by electing a new primary. Now, here is the view change protocol. So, as I mentioned earlier that here say assume that this black node is the node that has actually failed. So, this node has failed. So, the other nodes will start this view change protocol. So, these view change protocols are initiated by the other replicas. So, they basically sends a view change message. Now, this view change message it contains certain parameter. One is this v plus 1, this is v plus 1 is the new view that I am going to propose for. Then there is n. So, what is n? N is the sequence number of the last table checkpoint s known to the node k, which is actually send this view change message. So, remember that before changing from one view to another view, I need to have a consensus among the replicas that every replica is on the same checkpoint. Well, because as we have seen earlier, PBFT works in rounds. So, it basically says that well, every replica have executed up to round n minus 1. Well, so that means up to n minus 1 messages that have been committed. So, we are moving to the message n. Well, so this n is actually the number of messages that have been committed. So, n number of messages have been committed. Now, this C that is a set of 2f plus 1 valid checkpoint messages corresponds to S. Now, whenever you have said that well, I have checkpointed up to message n, that basically means you have to give a proof. Well, it might happen that one replica say R4, it is in a slow network and it has not heard of the message n and it has received checkpoint up to n minus 1. Well, so what it does? So, it understand that well, n has also be checkpointed. So, I should update n, but to get that it also need a proof. Well, so this 2f plus 1 valid checkpoint messages, checkpoint message means my final commit message that we send to commit a particular message. So, this 2f plus 1 valid commit or rather you can say it is a combination of the prepare and the commit messages. Well, so this is basically being sent as a proof that well, this particular node has reached up to checkpoint n, that means up to message sequence n that have been committed. And P is a set containing a set PM for each request M that prepared at k with a sequence number higher than n. That means it might happen that up to n you have checkpointed, that means you have received the commit message, but for messages n plus 1 and n plus 2 you have received the pre-prepare message. Okay. But for these messages you have not received any commit message. Well, so if that is the case, that means you have heard of these messages, but this message has not been checkpointed or this message has not been committed. Well, now because this message has not been committed, you also sent an information about these messages. Well, that is the messages that has not been committed. So, that means these two particular set C and P, that contains the information that what messages have been checkpointed so far and what messages has not. Well, and N is the sequence number for the last table checkpoint message. Now, once you share this information and you see that with this information N, C and P, every replica can come to a common view that well, we have reached checkpoint up to message N and these are the set of messages that have been checkpointed. Well, and these are the set of messages that have not been checkpointed. That means, for them we have received the pre-prepare message or maybe we have received the prepare message, but we have not received any commit message. Well, so that way they come to an agreement about this individual messages that have been shared. Now, with this, whenever this information have been shared with the nodes, then the new view is initialized after receiving 2f plus 1 view change messages. So, you know that 2f plus 1 is the quorum for PBFT. So, you wait for such 2f plus 1 view change message. So, when you receive 2f plus 1 view change message, you have reached the quorum. So, you initiate a new view. Now, you select the next primary. Now, how to select the next primary, that is not discussed in PBFT, that is basically depends on the implementation. So, what you can do, that you can apply a round robin algorithm to select the next primary. So, that is basically used in Hyperledger Sawtooth. It uses a round robin algorithm to select a primary from the replica, and it is predefined that well, if replica R fails, then replica R plus 1 is going to be the next primary. Or you can use a leader election mechanism. So, that leader election mechanism can run Paxos or Paxos kind of protocol to select a leader, and based on that leader election you can move to the next view. You can select one node as the primary. Well, so Hyperledger Fabric basically uses such kind of leader election to select primary. Well, so once the nodes have received this view change message and they select a primary, then they send a view change acknowledgement message to this newly elected primary. So, here say R1 is the newly elected primary. So, these view change messages are sent and quorum is formed on these messages, and this new view and it finally sends a new view message. So, this new view message is the final message that is broadcast from the newly elected primary to other replicas, and this new view message actually ensures to initiate a new view in the system. So, this is the kind of setup protocol, that is set of messages that is being transferred from individual nodes to initiate a view change. Well, so initially there would be a view change message followed by this view change ACK once you have received 2f plus 1 view change messages, and once this newly elected replica it receives this 2f plus 1 view change ACK, that means reaches the quorum, it then sends this new view message. This new view message actually helps to initiate a new view in the system, okay, and the system moves from view V to view V plus 1 with a newly elected primary and then starts the PBFT algorithm in rounds, the same PBFT algorithm that we have discussed earlier. So, in conclusion, what we have seen in this lecture, that PBFT is safe under 2f plus 1 quorum over an asynchronous environment, but liveness is affected when the primary is faulty and we cannot ensure liveness in a pure asynchronous environment. So, PBFT runs a view change algorithm to elect a new primary when the primary is detected as faulty. Well, and this view change protocol, it works on a weak synchrony assumption. So, this gives us a kind of overall view about the Byzantine fault tolerant algorithm and how Byzantine fault tolerant algorithm is used in PBFT to reach to a consensus in the presence of Byzantine faulty node. And as I have mentioned that many of the hyperledger platform they use PBFT to reach consensus. One of the prominent example is Hyperledger Fabric. So, you are going to look into or going to have a tutorial on Hyperledger Fabric within the next few lecture. So, you will learn that how you can run your own smart contract on top of Hyperledger Fabric, but at the end of the Hyperledger Fabric or rather at the back end of the Hyperledger Fabric you have this PBFT algorithm which is running to reach consensus in the system. So, that is all about this lecture. Thank you all for attending. See you all in the next lecture.